just doing this again? I had on the homework that is due on Friday. I'm going to push that back to Monday. Yep, you're welcome. Also, remember we have a test next week. Right? First test next week. So, again, you can do it either Thursday or Friday. Doesn't matter which. Just schedule a time with me. Either day is fine. We won't have class on that Friday either. I would never make you have a class on Saturday if you're outside of class to come take a test. So, if you wanted to, the only reason why I'm doing it outside of class is that time's not a factor. So if you wanted to come in, say 8 or a little after 8 on Friday, and then have our class time to work through it, that's perfectly fine. Anyway, because I'm here by 8 anyway. So, any questions on anything at all? All happy? Okay. All right. Well, let's continue on talking about our discussion of matrix arithmetic ideas. Pardon me. So one of the last things we wrote down last time was different properties that matrix multiplication has with respect to distributive properties or associative properties. So let's see if we can prove the associative property for multiplication, mainly so that we can play around with a little bit the notation that we use when we're multiplying matrices and looking at the general entries. In particular, so that I have an example here in class. I've got a video example with distributive property over addition from the left-hand side, and on the homework I'm asking you to prove it from the right-hand side. So with a couple of examples, you'll see what you need to do for that particular proof. So again, for associative property, we want to show that we can regroup our multiplication. Either put the second two together, multiply those two together first, and then multiply the first, or multiply the first two together, get that answer, and then multiply the third. Again, if I'm writing this down, I'm assuming that all these matrices are able to be multiplied together, so all the dimensions all make sense. So in order for the B times the C to be defined, we need to make sure the number of columns of B matches the number of rows of C, right? That answer will have number of rows that equals number of rows of B. So we need to make sure the number of columns of A match the number of rows of B. Right? So when we start this proof again, I'm going to start by writing general entries for the three matrices that we have, the A, B, and C. And we'll denote what the dimensions of each one need to be in some general sense, but making sure that those different dimensions match up. Okay. So we'll let A be A sub ij. If that's an M by N matrix, then we just said that the number of rows for B has to be what? In order N. Good. So I'll call that N by P. Just going down the alphabet and skipping O because it looks like 0. And C sub ij. What do you think we should say that for the dimensions for that one? P by Q. Good. I guess I forgot a conjunction there. I should say and to that, but that's okay. All right. Again, this is just giving me a way to reference the general entries for each of the three matrices. And again, like I mentioned last time, if I want to do an arithmetic proof for matrices, I want to try to see what the general entry for the left-hand side looks like. So get it all the way down in terms of the A, the B, and the C. Do the same thing for the right-hand side. Get it down in terms of the A, the B, and the C, and see that they're equal, or argue why they have to be equal. Probably a better way to say it. All right, so if we're going to work together on the left-hand side, what two matrices do we multiply together first? The BC, right? What size does BC have? N by Q. Good, yep. And so the N by P, P by Q makes an N by Q after we multiply. And then remember that, goodness gracious, remember that the entry for the product has that funky form with a summation, right? So we'll have K equals 1 to, what's the upper limit? What does it run through? The P, right? So it runs through that common number, right? So it'll be 1 to P, and then it'll be B sub what? IK and C sub KJ. Good. So again, remember, the reason why we have that summation is, of course, that we have to do the sum of the products of those entries when we do our matrix multiplication. We run across the columns of the first at the same time we're running down the rows of the second. So that's why we use that P as our upper limit, our index there for our sum. All right, so we've multiplied B and C together. So the next thing we need to do is what? Yeah, multiply the A. Good. What size does this matrix is this matrix going to have? M by Q, right? We're doing the M by N and the N by Q and putting them together. So we'll have M by Q when we're done. Again, we're multiplying two matrices together. I think it's easier to write it first, and this is why I always make those kind of intermediate steps. It's easier to write this general entry in terms of these two first, and then make your substitution, as opposed to trying to write it all at once. Use your A and your D together first to write the general entry, and then substituting what the D has to make. Okay? So what, using the A and the D, what do your F's have to look like? Okay, I think I'm going to use a different letter since I'm using a K already up there, so I'll use a L, for lack of a better letter. Okay. And then it runs to N. Good. Because again, it's what matches in the middle, right? A is M by N, BC is N by Q. So the N is what we're running through our index. What goes inside here? So the A sub I L, because that's the index we're using now here, right? And then, yeah, D sub LJ. Good. The reason why I want to make sure I use a different index here is because I want to make a substitution now, and this has that K in it, right? And those indices don't have anything to do with each other. The letter doesn't matter what I use as long as I'm not using some other letter that we've already used. Okay. That's the important thing. All right. Now, again, the idea that I told you yesterday and told you earlier today is I want to try to rewrite everything in terms of our original matrix, right? What can I substitute in for this? Yeah, this first summation here, right? Except that instead of an I here, I've got a L. All right, so what's that going to look like when you make that substitution? So the L one is just in for the I, right? So BK J, good. Yeah, because the L just went in for the I. So it's B sub LK rather than an IK. Because we just replaced the first subscript with an L. And just to emphasize here, I'm going to put parentheses here. We'll start with we've gotten now to the point where, pardon me, we've gotten now to the point where we've got everything in terms of the general entry for A, general entry for B, general entry for C, for the left-hand side, right? I say A, B, C. Good? Okay? Let's stop there, and let's go work with the other side and see if we can get down to the same point, and then argue why they're equal. Okay? All right, so if I want to work with the right-hand side, what product are we going to work with first? AB, good. What am I on, letter G? What's that? We're gonna, I think we only need one more. Now, again, at the end here, I want to get to showing that the left-hand side and the right-hand side are the same. In particular, to be helpful, if I can make my indices match now, rather than trying to resubstitute things in later. Okay. So here's what I mean by that. Notice I'm taking the A times the B here, right? Notice that your middle index for your A and your B is what? It's the L, right? That middle index is L. So let's write this in terms of the index L rather than a K. Okay. Where does your summation stop? What's that top number going to be for multiplying A and B together? The N, right? Because it's the one that matches in the middle. This is why I said, let's go ahead and use an N here. Or excuse me, use an L here, because now notice I'm getting the same summation here. What goes inside? A sub I L. What's next? We're multiplying A and B together. B sub LJ. Good. All right. Now let's multiply AB times C. I forgot to write down what the size of the matrices are. Your AB, would be what for your A times B? M by P. So then this matrix AB times C is going to have M by Q. Is that a good sign, by the way? Do we want it to be M by Q? Yeah, because notice the left-hand side here was also M by Q, right? So it's a good sign that we got M by Q. All right, so again, I think it's easier to do it a step at a time. We're doing AB times C. So let's write this in terms of the G sub ij and the C sub ij first, and then substitute. Okay. What index do you think you want to use on your summation this time? If we're really trying to show the left and the right side are the equal, what index do you think you want to use here? The K, right? Because the K is the one that's on the C, isn't it? So K equals 1 to, where does it stop? P. These are all good signs, right? Looking for what we already did in the previous one. Again, using your G and your C, what do we have? I can't hear you, sorry.
It's the summation of L equals 1 to N of A sub I L.
Okay. Yeah, so let's do it a step at a time. Let's just use the G. So what's the first one going to be? You're right. You're going to plug it in. So, okay, good. And then Good. Yep, exactly. All right, the G is on the left now. Right? Again, looking at what we're trying to get to, is this good that we have C sub kj? Yeah, because I see that here, right? You don't want to lose sight of the forest because you ran into a tree. Okay? All right? Keep track of where you're trying to get to. This is what I'm trying to show you that it's equal to. I wouldn't want this thing to have some other subscripts in it. Right? Okay, so it's good check as we go along. And then Laney was just telling me what to plug in for the G sub ik. What do you plug in for the G sub ik? You were just telling me a second ago. Now you're all shy. What did you tell me? Okay, so notice that we're doing a G sub ik now, right? So instead of LJ, we'll have LK. Good, yep. Oh, and I lost my C. This is on this side. So again, we're just taking this whole summation here, plugging it in for the G sub ik, but notice my second subscript has changed. So we changed the second subscript where we replaced the J with the K. Try again. Don't worry. This was IK, so we replaced the J with the K here on the end. Notice that do our subscripts all match for what we had? Just our sums are in a different order, right? Okay. All right, but now notice we've got everything now is in terms of numbers. We're out of matrix land, we're in number land, right? So relative to, let's go back up to the first one. Relative to this sum, what can you do with the A sub IL? Distribute it. I can move it to the inside, right? Right? Relative to this sum, what can you do with the C sub kj? Distribute it again, right? So we have our F sub ij, start with there. This is, I'll just go ahead and distribute it. A sub il times B sub lk C sub kj. Right? That's what we would get if we just distributed it on the inside. What would it look like on the other one? Going the other direction. Got to distribute this in here. So I got a double sum, don't I? The outer one's going to be, the K from 1 to P. The inner one will be, the L is 1 to N. And then on the inside, we'll have A sub IL, B sub LK, C sub KJ, right? What's different? What's different about these two entries? Should be two things that are different about the two entries. Yeah, the summation is flip-flopped, right? But what are we adding together? Are we adding matrices or are we adding numbers? Just numbers, right? What do you know about real number addition? Doesn't matter the order, right? I can flip it around. So we can flip the summations around, right? What else do you know is different? Yeah, the parentheses, right? But what do we know about real number multiplication? It's associative, so the grouping doesn't matter, right? So here, I could regroup here, I could reorder, and they'll meet in the middle, right? So I can write this as sum L equals 1 to N, sum K equals 1 to P. I'll regroup the first one. In the second one, I didn't move myself into enough room, did I? In the other one, I'll just reorder the summation. So again, the reason for that inequality, that equality, the reason why we can say those two things are equal, in the first case, we're using real number. Did I actually reassociate? No. Oh, no, yeah, I did. Sorry. I don't know why I put an extra thing in there. I didn't need it. I'm saying the exact same thing in both of these things, right? Here, going from here to here, we're using real number multiplication is associative, right? Going from here to here, we're using real number multiplication addition is commutative, right? I didn't need to write it twice. It was the same sum both ways, but just to illustrate what we were doing, going from here to here, I flipped the summations, right? From here to here, we were grouped what's inside the summations. But now they're exactly the same. And remember, to show that two matrices are equal to each other, we need to show they have the exact same entries. Is that what we just showed? Because the F is representing the general entry for A times BC, and the H is representing the general entry for AB times C. So therefore, the other way around, I guess is how I have it written above. To get your associative property verified. I know, it's a lot of symbols. But we're just playing around with the properties. And again, the whole point of this is basically all the types of problems that you saw before doing algebra kinds of things, you're trying to break it down into smaller pieces. And that's exactly what we're doing here, right? Instead of dealing with the matrix as a whole, we're dealing with each individual entry all at the same time, but we're breaking it down into the entries and then showing that the entries actually have to match up. So pretty common technique in math to break things down into smaller pieces. That's what we're doing here. I know it's a lot to take in, but any questions on how we got there? Yeah, thanks.
So if we were writing this proof ourselves, would we have to write that like real number multiplication is associative and stuff, or is that just like
you should? Yeah, that was you should know.
Okay.
I mean, it should be fine to be able to do that. You don't have to write it. So the one that you have to do, you're going to use the fact that real number multiplication is distributive. So you'll just distribute it across. Same idea. That one won't be as bad because with the distributive property, you're only doing one product on one side. The other side is two products, but you can use the same index on both of them. So that one shouldn't be as bad. This one's kind of ugly. I'm not disagreeing that one's kind of ugly. There's a lot of things to keep track of. Like I said, I'm expecting you to do one of these on the exam. Okay. Not anything that's horribly onerous, but just to make sure that you understand about playing with the entries. All right, so pardon me. A couple other properties that we talk about as far as matrix multiplication. Yeah, this is all with matrix multiplication, and then we'll do one more operation with a matrix, and then we'll get into inverses today. So one more special type of matrix is referred to as the identity matrix. We already talked about the additive identity for a matrix, where we had the matrix of all zeros. That gives us an additive identity. The idea behind a multiplicative identity comes from the fact that we are interested in algebra. So we're interested in solving equations. If you want to solve the equation, say 3 times x equals 9, I need to multiply by 1/3, divide by 3, right? Agree with that? Okay. And it makes a 1 on the left-hand side. So that way I have 1 times x equals 3. And so then I know 1 times x is the same thing as x. We have that multiplicative identity idea, right? Okay. So that's where the identity matrix idea, multiplicative identity comes from for matrices. When we have an identity matrix, we want that thing when we multiply it by a matrix on the left, we don't change the matrix at all. We multiply it on the right, we don't change the matrix at all. Okay. So here's how you define the n by n identity matrix. We'll denote it with I sub n if we want to specify what the dimension is. If it's understood what the dimension is, we'll just not put the n on there. We only need to specify the n because the identity matrix is always square. It's always n by n. Okay. I'll write it more like this first. The identity matrix is the matrix where we have 1s down the diagonal and 0s everywhere else. This is an example of what we refer to as a diagonal matrix. When we say diagonal matrix, we're talking about a matrix that has 0s everywhere that's not on. This is what we refer to as the main diagonal here. Notice that on the main diagonal, your subscripts denoting the entries will be the same, right? This is the A11 entry. This is the A22 entry. So on down the line, the ANN entry. So one way that you can denote this with a general entry, and this is why I haven't been using e's, because we use it special for things that look like identity matrix. So we use an EIJ typically when we're referring to the identity matrix and talk about that. It's 0 if the subscripts don't match, and it's 1 if the subscripts do. Okay. So going and appealing to these general entries of these of the matrix, you can show that this really does give you back the same matrix that you started with. Okay. So doing this generally speaking, if I wanted to do I sub n times A, let's suppose that your A was written as A sub ij this way. Let's look at what the general entry looks like and see that we get the same thing back again. Okay. Again, using how we define matrix multiplication, what do your C sub ij's look like here? If I call the general entry of I sub n times A, C sub ij. What does your general entry look like? Yeah, k equals 1 to, it better go to n because I is an n by n matrix, right? What goes on the inside here? E sub I k, A sub kj, right? The E is on the left, the A is on the right, so the K in the middle. Column for the E, row for the J, or the K, the A. Good Lord. All right. Let's see what this would look like if you were actually to write it out longhand. Okay. If we were writing this out longhand, notice the thing that's changing is the K, right? right? That's the thing that's changing is the K. So the first one would be EI1A1J. What would the next one be? What would be the next term in the sum if you're writing it out? EI2A2J. The next one would be EI3A3J. And we would keep on going until we get to what? Yeah, EIN ANJ, right? EIO. No, sorry. That's what it felt like as I was going along. All right. We're going 1, 2, 3, all the way up to N. Somewhere in the middle, we have to hit I, don't we? The I and the J both have to be between 1 and N. Well, the I has to be between 1 and N. Right? So somewhere in the middle, I have an EII AIJ. Now, the way the identity matrix is defined, what are all of these ones that are EI1, EI2, EI3, all the way out to EIN equal to besides the EII? They're all 0, right? Oops, write it this way. 0 times A1J plus 0 times A2J, so on out to 0 times ANJ. The only one that survives is what? The EII, right? The one in the middle is 1 times AIJ. So what does that simplify to? Just AIJ. So notice when we multiply the identity matrix by the A, the general entry here matches, right? The CIJ matches the AIJ. It doesn't change the matrix at all. That's what we're showing here with symbols. But that's what we're showing. We didn't change the general entry at all. It stayed the same as what the A was. Again, you need to make sure your matrices are multiplicatively conformable. So my A would have to have n rows. It could have any number of columns you wanted. A doesn't have to be square, but I does. And you may use a different identity matrix on the other side, depending if you have a non-square matrix, you use a different size identity matrix. In any event, the whole point of this is that when you multiply by the identity matrix, it doesn't change the matrix at all. So it acts like the multiplicative identity, like 1 does for a real number. The idea behind that, again, is one of the things that we're going to be interested in the next section is solving matrix equations. To solve a matrix equation that involves multiplication, I need to undo that multiplication if I can. I need to get back to the identity. Just like you do when you solve the equation 3x equals 9. Okay. So we'll talk about how we undo that in the next section, and when we can't undo that. Sometimes we just can't undo it. Okay. All right. So anyway, that's what the identity matrix is. There's one more type of matrix I want to talk, one more type of operation we're going to talk about, and then we'll get into inverses. But are there any questions about identity matrix at all? We'll understand a little bit more about why we want to talk about it in the next section. But is it okay to understand what it's doing? It's just acting like 1. That's the whole point. Okay. All right. The other type of matrix operation that pops up is what's referred to as the transpose of a matrix. And rather than writing it in terms of general entries in the operation, I'll do an example, and then we'll just talk about different properties that it has. So let's start with the matrix 1, 7, 2, 0, 8, -6. When you do the transpose of a matrix, you flip-flop rows and columns. Rows become columns, columns become rows. Okay? So in this matrix, the first row is 172. So in this matrix, the transpose, the first column will be 172. First row, or excuse me, second row is 0, 8, negative 6. So the second column is 0, 8, negative 6. So you literally just start flip-flopping rows for columns. If you like thinking about it visually, this is the main diagonal here. We're doing a reflection about that main diagonal. So think about, here's a horizontal line. We're making it a vertical line. If you don't like visual, don't ignore what I just said. But that's what you're doing. If you think about it from a graphical perspective. Remember when you do inverse functions back in algebra class? That's kind of that reflection idea. I think it's just easier to go across your rows and just write them as columns across and think of it that way when you're doing it, rather than thinking about it visually. Like, I'm not very visual, so this doesn't help me, but it helps some people. All right. Anyway, that's how you do transposes. So you can define it in terms of general entries and do similar types of proofs of properties, but I'm just going to write what the properties are to help us out rather than doing a bunch of proofs of the properties. So some of them you can just think about why it's true. If I do the transpose, so the notation is it looks like a superscripted or an exponent. It's just telling you to do the transpose. If I do the transpose, and then I do the transpose again, what do you think I end up with? Hey, yeah, start back where I started. Good. If I flip rows and columns, and then I flip rows and columns again, I end up back where I started. Okay. This one, if I add A and B together and then flip rows and columns, what do you think we could do instead and get to the same place? Flip them first and then add them, right? Because everything's going to match up component-wise anyway, right? You could add first and then flip, or flip first and then add, right? So I always hesitate with this one. The students love to distribute exponents over sums, which doesn't work, right? Okay. Or roots don't distribute over sums, all those kinds of things, right? Okay. But in this case, it looks like an exponent is distributing over a sum. But the transpose isn't an exponent, it's just a notation. How about this one? This one says multiply the scalar through everything and then flip. What do you think you could do instead? Flip it and then just multiply the scalar through, right? So I can move that scalar out in front like that. I don't need the parentheses on the right-hand side. But that makes sense, doesn't it? Those all make sense, I think, if you think about them, right? When you add, you're just matching entries up, so it doesn't matter if you flip first or not flip first. You're going to get to the same place. This one, you're just running a number through all of the entries. Does it matter if you flip first or not? No. Okay. All right. The last one is the one that requires a little bit of thought, and the proof is not something I'm going to go through. All right, but let's think about why it's not this. Don't write this down because I'm going to erase it in a second. Okay. This is what you're used to with distributing an exponent over a product, right? Just take it to each one and call it good. Like AB squared is the same thing as A squared, B squared. For real numbers, it doesn't work for matrices. But that's what you're used to, isn't it? But let's think about it in terms of the size of the matrices and see if this makes any sense. So let's say A is M by N. And then I made it minimized. That was weird. And B is N by P. Then what does AB, what size does AB have? Good, M by P, good. Now let's do the transposes. What size does A transpose have? N by M, right? It's flipping them around. Okay. B transpose is P by N. Can I do that? No. Okay. So it can't be A transpose, B transpose. But which order can it be? It could be B transpose, A transpose, can it? Because the ends match. And that's actually the property. So going back up here, this is why I said don't write that down. There is a property, it's just the other way around. It's the product, the transpose of a product is the product of the transposes in the reverse order. It has to get flipped around. That was not a proof that we did. We're just showing that the product in the reverse order is actually defined. If you wanted to prove it, you would go through and show the general entries of the same on both sides, just like we have everything else. So again, these are properties of transposes that pop up. We use right now. We're just playing around with basically arithmetic type properties of matrices. Later on, we will see applications of transpose matrices. In particular, one of the applications we'll do later on with least squares involves doing a transpose of a matrix. All right. Any questions about the operations at all? I know we've been a little proof heavy, but the operation's okay. Being able to add, being able to multiply, flip a matrix around. All right. So let's talk just briefly, start up the next section, 2.3. Which talks about the inverse of a matrix. So again, the idea here is that if we have a matrix, remember we talked about how we can rewrite a system of equations as a matrix equation, right? So we talked about one way to describe a system of equations is to write it as the coefficient matrix times the x vector is equal to the column vector, right? If we matched this with that idea of trying to solve the equation, say 3x equals 9, notice that again we would try to undo multiplication by 3, right? You do the 1/3 on both sides. And so on down the line, right? That's what we're trying to do. Notice that there is actually some honest to goodness algebra going on here, right? Notice I multiplied 1/3 on both sides. I actually have to reassociate. And then make that a 1. And then know that 1 times x is x. I know it's a simple one, what they refer to as a one-step algebra problem. There's a lot of things involved in that one step. I have to know that the inverse exists. I have to be able to reassociate. I have to be able to understand what an inverse is, and then I have to know what an identity is for a one-step equation. This is why kids have a hard time understanding math. They call it one step. Boo hockey. There's 4 steps in there. From an algebra perspective, there's 4 steps in there. You just don't ever write them down. Okay? This is why algebra is hard for kids. One of the reasons why algebra is hard for kids. Okay? But there's a lot of things in there. Anyway, so we're going to try to apply this exact same idea here. I need to be able to, the idea is, can I undo this multiplication and go to the other side? Sometimes the answer is no. Okay? Sometimes the answer is just no, I can't undo it. All right? To give you an example of a multiplication that can't be undone, what do you get? Oops, not 1. If I multiply these 2 matrices together, what answer do you get? I get 0. I get 0 all the way across, don't I? You match your rows and columns. Now, does this ever happen in the real numbers? Are either of these 2 matrices the 0 matrix? No, the 0 matrix says you have to have all zeros. So now I've multiplied two non-zero things and got 0 out. All right? Anytime you multiply two things together and give you 0, you can't undo that. Because I don't know what I started with. That's why you can't divide by 0, by the way. I don't know what I started with. All right? Division by 0 would say, what did you multiply by? What did you multiply 0 by to give you 0? I don't know. 7 pi negative 3, right? You can't divide by 0 because there's not a unique inverse. I don't know. I can't undo that. Once you multiply by 0, you're screwed, right? You can't undo it, okay? So it's the same idea here for matrices. I can't undo this multiplication because I don't know what I started with. There's lots of things that you could multiply together and give you 0. Okay? So you really just can't undo it at all. So, but we're interested in when we can and how do we do it. That's what we're interested in, right? So our goal here is to multiply both sides by something here that gives me the identity matrix. Okay? That's our goal. So we're trying to find, now again, to do inverses, the matrix has to be square, because I want the inverse to work on both sides. So for my definition here, a square matrix A has an inverse B if A times B is the same thing as B times A is the identity matrix. Technically, we refer to this as a two-sided inverse. If you get involved in non-commutative algebra, you can talk about one-sided inverses. Something works on the left, gets you back to the identity. Something works on the right, gets you back to the identity. It doesn't necessarily have to be the same thing. I'm a commutative algebraist because non-commutative algebra is hard. Okay. Not that necessarily commutative algebra isn't. It's just my brain can't wrap around my multiplication not working both ways. Okay. All right. Anyway, this is what we mean by an inverse. That's the idea. So again, here if you have an inverse, you multiply both sides by that inverse, and you end up with getting x by itself. Okay. The whole goal of finding an inverse is to do that operation, undo that multiplication by a. Okay. So mainly what you're trying to do, if I think about what you would need to do, if I want matrix times an inverse to be back to the identity, well, think about how you multiply matrices together. Let's say if I take, and I'm going to just do this real quick. I know I'm out of time. We'll talk more about this on Friday. If I take a matrix A, whatever it happens to be, and let's think about what we're multiplying here by columns. Let's just say that this is column 1, column 2, column n. Okay. Write it that way. I know we're writing those vertical lines there just to denote that I'm doing this by column. Okay. Think about what happens when you multiply these things together. The first row of A gets matched with column 1. The second row of A gets matched with column 1. Third row of A gets matched with column 1 all the way down, right? And that's how you form the first column of the product, isn't it? Same thing with the second, same thing all the way out, right? So I can think of this as being A times C1 in a column, A times C2 in a column, A times Cn in a column, right? I can just think about multiplying the whole matrix times the first column, make that the first column. Whole matrix times the second column, make that the second column, and so on down the line, right? If I want this matrix to be the inverse of A, well, we'll talk about the inverse next time, but what does this first column have to be? If I want this times this to be an inverse, this needs to be the identity matrix. What does this first column need to be? It's going to be the 1 here and zeros all the way down, right? Because remember, identity matrix is 1 in the upper left-hand corner, zeros below it. What does this column have to be? 0, 1, zeros below it, right? All the way down to zeros to 1 down below it, right? This looks like a system to solve, doesn't it? A times some magic vector C1 equals 1, 0, 0, 0, 0. You know how to solve that. Doing row reduction, right? Same idea here, same idea here. So we're going to talk about how we can find these columns using row reduction. That's how we're going to find an inverse matrix. Okay? Basically, we've got n systems of linear equations to solve. We'll just do them all at the same time. We'll do that next time, and then talk about some properties of inverse matrices. So have a good one. See you on Friday, if not before. Some of you I see tomorrow.